Hello, students. We are into section 8.2, talking about what are known as equals, relation, and equations. And I think it's probably interesting to talk about the idea of a relation before we get into these specific ones. So there are many different relationships in this in this class, but when we talk about a relation, there are oftentimes ideas that go along with those. So what I'd like to do is talk about some of the properties of those. And so we'll take a look at how they work with equality, and then we'll introduce, I guess, a little bit of strangeness, but how they relate to other relationships. So let's start first by talking about this concept that you see on the screen, and it's called the reflexive property. So in order to be reflexive, first off, we have to have a set. Okay, we'll have to have a set, and we know about that from Math 105. So let's say whatever's in the set. Okay, I'll put 4 things in the set. And then we'll have a relationship, which I'll call R. And if something is reflexive, then here's what R does. R, when you think about these points, here's A, here's B, here's C, and here's D. The relationship will be like a little arrow. So what I want you to do is picture this. The relationship, if it's reflexive, it means the object relates back to itself. Now you can picture that maybe best with the idea of equality, because whatever value I pick, A is equal to A, like the number 7 is equal to 7, right? I mean, all of these things we kind of understand with equality. So that's one way to think about reflexive. What are some other relationships that are reflexive? Think about is the same age as, okay? Is greater than or equal to, that would be another one. Is as tall as, right? Is dating, is married to. All of these things are relationships that we would consider reflexive because every object would be related to itself. Okay. So there's plenty of pieces. I don't think I said is dating. I mean, you're not dating yourself. I need that one for the next one, but I'll get there in just a moment. So if person A is the same age as themselves, person B is the same age as themselves, person C is the same age as themselves, person D is the same age as themselves. That's what reflexive means. Okay, so reflexive has a definition. If A, maybe I'll choose X. Let me take that out. If I'll have to pick any element of A, then X relates to itself as an element of the relation. This is the definition of reflexive. Okay. So that's what it means. Pick any number in the set, pick any element in the set, then it relates to itself. Okay. Then we come down to the idea of symmetric. So let me erase these over here. I'm going to keep the points the same, but I am going to erase the arrows only because symmetric may not look exactly the same. Okay. So now let's take a look at what's known as symmetric. The symmetric property says this: if X and Y are elements of A, then X related to Y being in R implies that YX is an element of R. So it is a conditional statement. Okay. And this is true for all. Maybe I should phrase that. Let me see if I can tweak that just a little bit, because it really is an if statement. So this, you could say for all, it's the same thing. For all X, Y, and R, if X, Y is an R, maybe I'll rewrite it as an if then, so it doesn't have as many symbols. Maybe that'll just look a little bit better. It's the same. The arrow is the same concept, but maybe this works a little bit better. If X, Y is in the relation, then YX is in the relation. Okay. And I guess I could do the same up here. So we can, I'll just make it existential. For all x in here, x is related to itself is in R. There we go. Okay, so what does this mean? It means if I have a relation, if something is symmetric, then if A is related to B, then B is related to A. And this is the one where I was going to say is married to would come in really nice, right? If A is married to B, then B is married to A. If A is a cousin of B, then B is a cousin of A. Okay. So there you go. But notice it's an if statement. It says if X, Y is in R. So notice A to C. I don't need to have one going from C to A because I don't have one from A to C. If I had this arrow structure right here, if I met the condition, I know we're coming right back to Math 105. If I meet the condition, so if it's true that I have a relationship one direction, then what? Then I have to have the relationship the other way. Okay, so then I have to have this one. If I don't have that green path, then this piece over here would be false, and you would say the symmetric property does not hold true for this relationship. Right? And lastly, transitive. Transitive says this: for all x, y, z in the set, give me three things in the set, then if x, y and y, z are in the relation, then x has to go to z is in the relation. Okay. So now let's come back over to our little picture here. Let's take a look at what this would look like. So notice it has a couple if statements. So if A goes to B, right? There it is. And then B has to go somewhere else, and B goes somewhere else. Then in order for this to be transitive, A, the starting point, has to also go to D. So if A goes to B and B goes to D, then A has to go to D. Now you can see this with equality, right? If Amy is the same age as Bill and Bill is the same age as Carla, then Amy is the same age as Carla. So there's a relationship that kind of helps kind of understand how that works. If Al is the same height as Bertha and Bertha is the same height as, who do I want to say, Carl, then yeah, Al is the same height as Carl. So again, we get this relationship, and this is known as the transitive property. Now, transitive property holds with equality, symmetric holds with equality, and reflexive holds with equality. And these three together, if it's reflexive, symmetric, and transitive, we call it an equivalence relation. And equality is our biggest equivalence relation. Okay, but it's not the only one. So let's talk about a few others. Let's talk about something like the idea of less than. Okay. Okay. So if A is less than B, does that mean B is less than A? And we'd say no. So this one is not symmetric. Okay. Is it reflexive? Is a number less than itself? And we would say no. So it is not reflexive. Okay, let's go to transitive. If A is less than B and B is less than C, does that mean guaranteed that A has to be less than C? And we would say, well, yeah. So this is a relationship that is not symmetric, not reflexive, but it is transitive. Okay. So here we go. Let's take a look. Maybe we can take a look at some pictures and kind of see what kind of a relationship we have based on these three rules. So over here, I'll draw a relation and let's see how we do. Okay, so first off, let's check reflexive. Do objects relate to themselves? And you could look over here and say, well, A relates to itself, B relates to itself. Looks good. But notice this has to be true for all of the elements in the set, and it's not true for C and D. So this would be reflexive, symmetric, or transitive, and I would say it is not reflexive. Okay. Symmetric. Symmetric says for all the elements in here, if we have one that goes to another item, so C goes to D, then we better have D going back to C, and we do. That is the only one that's there, so symmetric is a yes. Now for transitive. So A goes to B, and B goes to C, then A has to go to C. Okay, well, let's take a look. We have A going to A, but that's it. Okay, so that one really doesn't go anywhere. So we could say, well, A goes to A and A goes to A, then A has to go to A, because it could be, just because we say X, Y, and Z in here, it doesn't say they have to be unique. So they could be the same, which A already goes to A, so that doesn't prove it wrong. Okay, so let's try this one then. And let's see if we can kind of follow the path along. Let me change color. Okay, so let's start with C. So C, so now C goes to D, right? And D, where does D go? D only goes to C. Okay, so here's my start, and there's my end. This says your start has to go to your end. And C has to go to C, but it's not there. It's not there. So it is not transitive. So the picture that I've drawn here is a relationship that is symmetric, but it's not reflexive and it's not transitive. Okay, if you wanted it to be transitive, I would have to have C going to itself, and I'd have to have D going to itself in order to make that transitive. Then it would be symmetric and transitive, but it would not be reflexive. Oh, actually, in this case, then it would be reflexive because all four of them actually work. This would be reflexive, symmetric, and transitive. Okay. Phew. All right. So there we go. So that's what we're talking about when they say equal relations. When they say equals relation, they're talking about an equivalence relation, something that is reflexive, symmetric, and transitive. See how it says for all real numbers? And this is using only the equal relationship. Now, we'll also use relationships like this when we get to geometry. So that's why we're building them now, right? If A is congruent to B and B is congruent to C, then by the transitive property, A is congruent to C. And if one line is parallel to another and then parallel to a third line, we could say the first and second lines are parallel as well. So we get a lot of fun pieces with relationships when we get into mathematics. Let's see here. These are the properties of equality. Now, these are more what we covered in chapter 7. So a little bit of a review. And all it says is this. If we start with two things that are equal and you add something to both of those, they retain their equality. And that is true for multiplication as well. Now, it's really true, guaranteed true for addition and multiplication. For subtraction, remember subtraction, because we're dealing with real numbers, you could be adding a negative number, which effectively is subtraction. So we really do pick up subtraction as well. We don't really need a property of subtraction. We don't really need a property of division. We just need this idea that we can multiply on both sides and it's equal. Okay. All right. Let's see here. Yeah, this one goes back the other direction. So you notice it says A plus C equals B plus C. If I start with an equation that has something added to both sides, then I can remove that from both sides. They call it the cancellation property of equality. Now, you really could look at this and say, hey, Scott, isn't that really just the same property as before? Because all I could do here is add the additive inverse. And so, yeah, you could add the additive inverse on, and you get right back down to say that A has to equal B. And that's what we get right there. Now, the only time that causes a problem, there's no issues with negative numbers, but there is a problem with multiplication and division because there is one number that you cannot divide by, and that's 0. So as long as you put a little caveat in here and say, as long as we're not saying this, because you got to be careful. Here's why. 5 times 0 is the same as 7 times 0, right? 5 times 0, 7 times 0, they're the same. So that meets the condition here. But if I then say, oh, then because they have the same value on both sides, we'll just remove that using what's known as a horrible way of saying it, the cancellation property, but that's what they call it. And you end up with saying 5 equals 7. You can see the problem here. So we want to be very careful. This works every single time except when it's 0. So if you meet this part and it's not 0, I guarantee you the next one's going to be true. Okay. And now this is one of the best properties of all. And this is one of the critical pieces in algebra. And again, I think it's one that may have been glazed over as some of you struggled a little bit with this in Math 105. If I multiply two numbers together and I get 0, what can you tell me about this? Okay. Is it possible for both of them to not be 0? And you'd say, no. At least one of them has to be 0. In fact, they could both be 0. So you could come down and say, well, Scott, I know that A is equal to 0, and I'm going to use the logic word appropriately, or B is equal to 0. And the or means at least one of those has to happen. And so this is a property of 0. And so we use this a lot in algebra as we go forward. It's known as the zero product property. Now, again, you've probably seen it in algebra where you were factoring something and setting it equal to 0. And you'd say, well, either the first one is 0 or the second one is 0, giving you the idea that there could be more than one solution to an equation. Okay, solving equations with one variable. Now, you can do this using what's known as an equation balance. And so if they're equal, then you kind of draw them like this. And even when you're dealing with young kids, they can see this idea of same weight or, the same level on a balance. So sometimes this visual right here can help. I'm going to show another way as well in this class called what I call the magic box approach. I think it's a pretty fantastic way to do it. As long as you know the order of operations, you can actually solve these very quickly. Okay. But let's see here. In order to go through and do it using the drawings and the pictures that they have here, you would start with your equation, 3x minus 14 equals 1. So notice what you do is you put things on both sides. You really picture it that way. Then to help balance things out and to make it a little bit easier, you would add 14 to both sides because you had a subtraction of 14. You undo that, and now you're sitting here with a 3x on one side and a 15 on the other. And this is where you use that property that says we could multiply both sides by 1/3. We could take 1/3 of them, which gives us x in one stack and 5 in the other. Okay. What's another way to do it? Another way to do it is to say using bars. This is another visual approach. I'll show my approach right after this one, but the bar approach says I have 3x and I take away 14 and it gets me to 1. So the 14, see that we've kind of taken away, right, is right here, but that's my 3x. And so you can kind of see, oh, well then you must have had 15 to start with. And 15 is 3x, as you could break the bars up and say, well, each x then must be 5. So again, different way of doing it, visual way of doing it. Okay, so here's my way of doing it, which again, I hope you like. If not, feel free to use any of the others that you've seen. Okay, so here's the idea. 3x minus 14 equals 1 is the equation. Now, in the past, you might have seen little puzzles like this. And to be honest, I love puzzles like this. This is one where it kind of flows through. So as an example, so I'm going to come right back to this one. What if I said, I'd like you to take a number here, like the number 7, and we'll multiply by 5, and then I'm going to add 2, right? And then I'm going to subtract 7, okay? So take a look. If you started with the number 7, you'd follow along and it would say multiply by 5, so it'd be 35. Add 2, 37, subtract 7, and you get 30. Okay? So this is kind of how you would do it. If I just do the operations as they appear. Now, notice what happens over here. What if, right? What if somebody said that your final answer over here was 45? Could you go backwards to find? Now, notice going to this direction would be subtracting 7. So going backwards must be adding 7. So you could come back and say, okay, that gives me 52. And then going backwards here, this is adding 2, so this would be subtracting 2, so that's 50. And then up here, multiplying by 5 that way, so going the other way must be dividing by 5, so my answer must be 10. So in order to use this approach, what you do is you take a look at what operations you have, and you start with x always, just kind of at the beginning. So if you just have a single x at all, this is going to work just perfect. So start with x being your magic number. What's the first thing I do to x in this expression? X times 3. Got it. So I'm going to put up here, multiply by 3. Okay. Then what do? Then I subtract 14. Got it. And what do I end with? It tells me I end with the number 1. So all you have to do algebraically is just go backwards. I know, it's kind of crazy, but all you'd have to do is just say, hey, let me add 14 and let me divide by 3. So if 1 plus 14 would get me 15. 15 divided by 3 is 5. So guess what? X equals 5. That's it. So again, you can just read the order of operations off as long as you undo it. That'll always get you the answer. So I think that's kind of cool. I hope you do too, if you find it helpful. And also what I like about it is it helps me, I can kind of do these in my head. I don't have to write them out quite as much. Okay. All right, so here we go. Now, again, this part using the algebraic notation is going to be grade 6. Using the balance scales, using other approaches without necessarily using variables, that will be grades 3 through 5 as well. It is integrated. Algebraic thinking is integrated into the curriculum. All right, so take a look up here. Here's equations. Again, if you see equations have x's on both sides, take a moment, get the x's on one side, and then you're ready to play. And as a quick tip, if you happen to have fractions and you are thinking to yourself, fractions, why? Take a moment before you get going and realize you are completely in charge of this. So if you wanted to, you could multiply both sides by any number anytime you wanted. So if this is equal to 33x minus 1/3, you could say to yourself, I don't really want to deal with thirds the rest of the time. So I'm going to multiply both sides by 3. And when you multiply 4/3 by 3, you just get 4x. No more fractions. Over here on the left-hand side, 3 times 33x gives me 99x's. Over here, 3 times 1/3 gives me 1. And you now, through the power of algebra, have transformed the equation into something that's probably a lot easier to work with. And there you go. Use that anytime you want. You could use this with decimals as well. I've seen somewhere we have like 0.2x minus 0.03 equals 0.052 or whatever it is, right? And you're like, oh gosh. Well, find the smallest number you'd want to multiply by. See, this is tenths, that's hundredths, and this is thousandths. Well, just say, you know what? Can I just not deal with decimals right now? Let me multiply by 1,000 on both sides. 1,000 times 0.2x becomes 200x minus 30 equals 52. Multiply everything by 1,000. Which one of these would you rather deal with? Probably the one with whole numbers. Okay. So a good little bit of review here as you're doing it. And then we get into application problems. The application problems allow you to create expressions, which can become equations, solve the equations, and then put it back into the wording of the original problem. All right. Let's see here. Well, there's one that they've got here in the book, which is solved right there. And newspaper delivery. These are the ones I think students sometimes are like, oh my gosh, it's so much information, especially when you have Tons and tons and tons. Okay, 3 children deliver all the newspaper. Abby delivers 3 times as many papers as Bob. Okay. So again, if I was doing this problem, I'd start jotting things down for myself. Well, Abby does 3 times as many as Bob. So if Bob did 10, Abby would do 30. So Bob and Abby have a relationship, right? So if Bob does 10, Abby does 30. So I put a 3 over here, and all of a sudden, A is equal to 3 times B. I have a relationship between those. Connie delivers 13 more than Abby. Okay, so Connie delivers more than Abby. So Connie, you see, is Abby plus 13. Another way you could think about this, right, is, well, I guess you could say it the other way. You could say Connie minus 13 is equal to Abby. That would also be fine. Okay. All right, so we have a lot of relationships here that we could use. But now it says the 3 children deliver a total of 496 papers. So now come up and write a little expression. Just say, hey, well, however many Abby plus Bob plus Connie together has to be 496. And then if you want, use some of these other components down here, right? Let's see here. Well, notice this one. C is equal to A plus 13. Okay, right there, right here. Well, here's C. And guess what? That is A plus 13. Okay. So that's 496, right? And here's B, and there's A. So I don't know about you, but I'm feeling pretty good. I got rid of what looks like one of the variables. It looks a little bit better now. And then look at this top one. This top one says A, wherever I see an A, that's equal to 3 times B. So there's an A. And here's another A. And all of a sudden, I don't have an equation that has A's, B's, and C's. It just has B's, B's, and B's. And then you can just combine them because these are like objects. So 3 B's and 3 more B's is 6, plus 1 more is 7 B's, plus 13 is 496. And if I remember my steps, if I want to use the magic boxes, I'd say, oh, I'd multiply by 7, then add 13. So I would take 496, and I'd subtract 13, and then divide by 7. And that would get me back to how many papers Bob delivered. And of course, once I know Bob, I can figure out how many Abby delivered. And once I know Abby, I know how many that Connie did. So this is the process of thinking that sets math apart from some of the other areas and disciplines. There you go. Okay. We get into the assessment next. So that's it for 8.2. Again, it's all about algebraic thinking. If you don't know what something is, represent it with a variable. But in this section, we also talked about the relationships. If two things are equal, we can add something to both sides. We can subtract something from both sides. We can multiply or divide as long as we don't divide by 0. So remember that as you go forward, and I think you'll be all right. That's it for 8.2. Off you go.